Okay, so we're going to think about what happens after a particular change begins in these scenarios. I think a couple of the questions that you've probably looked at home, you've seen things like one of them will have hit the floor, or it might say something like the string breaks. So there's something that appears to be quite normal, and then something happens. And then there's some different things that happen here. So I've got a scenario here. I've got two particles. The mass of B is 5 and the mass of A is 2. And I've said that B is starting 1 meter above the ground. I need to think about, after B hits the floor, what happens next? Then I want you to think what happens to A. And I want you to try and describe those things using as much mechanics language as possible. So instead of saying, oh, B moves down and A moves up, I want you to try and say some things to me about what's their acceleration like, what changes about the speed, what's actually happening in this kind of situation, okay? And then we're going to try and go through and work out various things in this problem. We're going to then try and find out, I'll come up with a question actually of what we're going to do. So I'm just going to want you to try and think about what happens here. Then we're going to look at an animation, and then we'll make some decisions together on this one, okay? So what do you think might be happening next in this scenario that we have? Talk to each other. I want to hear, what do you think? I want to see how you might answer these kinds of questions. What do you think is going to happen next? You don't have to say, you just talk to each other and say, what do you think might be happening? Those questions in that black box there. They're not bouncy, no. We're going to presume that as B hits the floor, it's done. Okay, good question.
Yeah, I'll forgive first of all, can it pick up? Back up and it goes.
No, it's just going to be B hits the floor, done. Yeah, of course. A is going to keep moving up, definitely. We're not assuming that, it's just it would, wouldn't it? Mm. Yeah. Okay, so right, I want to hear some predictions, and then we're going to watch an animation of it, and then we're going to see what happens. Okay, we're going to see if we're right. So let's think about what is going to happen after B hits the floor. B is not going to bounce back, by the way. We're going to say that B hits the floor, and that's it. It's done. Red one, what do you think might happen to after B hits the floor? We can't think about B anymore because it's not moving.
A is going to go 1 meter up.
So when B has travelled down 1 meter, that's a really good point you've just made. When B has travelled down 1 meter, A will have travelled up 1 meter. That's an important observation.
It's going to go up even more a little bit.
Then it's going to go up more a little bit.
And then it's going to come back down again.
And what happens when it goes up a little bit more and it gets to the peak? Can we try and use some mechanics language here? Okay, good. So when B hits the floor and A moves a bit more, the string becomes slack. The string loses its tautness, okay? So the string loses its tautness. If a string is loose, how much tension has it got? None, it's got 0. Okay, that's important. What was making A accelerate? Okay, so the B was creating tension, and then what was making A accelerate? The tension. Although it was the weight of the B, it was actually the tension. If you were A here, you wouldn't, and again, I'm asking you to imagine being a particle hanging on a string, you wouldn't think, oh, there's a weight over there that's making me move up. You would think this rope is making me move up, okay? So when B hits the floor, and Shahan just said that the tension goes, what's making A accelerate now? Its own weight. Does that mean it's still accelerating up? It's decelerating. Okay, so as soon as B hits the floor, A will be slowing down, which accounts for what Red One just said. He said when A gets to a meter up higher, it's going to go up a bit. And when it gets to the peak, what do we know about it when it gets to the peak? No, the deceleration will still be the same, but the velocity will be 0. And then it would come back down again. Okay, so we're going to explore that whole scenario. And the beginning scenario until B hits the floor, we know all of the information about that already. The new part of the scenario is what happens after B hits the floor. And Shahan pointing out that the tension disappears is crucial, because there might be some other scenarios where we say the string breaks. If the string breaks, the string is loose, and that means that there's no tension. Very, very important. So let's watch the animation, and let's see if we can confirm everything that we've just said here, if this decides it wants to open. Fascinating. What's going on with this? Still loading. The internet's been really slow at school today because it's raining. Should I just try it and refresh it? Oh, no, look. Okay, so here we go. These are the two masses. They don't have the labels on them anymore, but whatever. So watch what happens when B hits the floor. First of all, the beginning bit of the journey when B comes down, we're predicting that A is also going to be accelerating at the same rate as B. It will move the same distance. As soon as B hits the floor, we're expecting to see the string go wobbly, as in like there's no tension in the string. And A, we will expect to see it slowing down because it's decelerating until it eventually gets 0 velocity at the top. And then it's going to speed back up, coming down again, okay? And then after that, we have to kind of stop because the animation doesn't do so much good after that, okay? So let's watch it. Let's not watch it then. We've got to refresh the page because I stopped the page, it didn't seem to do it. What a shame. All that build up to it, and now I'm having to refresh the page. What is wrong with this today? Okay. This is really annoying me. I wonder if I can just put that on a website on my phone, seeing as it's not working. GeoGebra, I'll put it on my phone and then I'll put it on the screen. GeoGebra.org. No, I can literally show it to you now. So it's FYY SXW 3S. Here we go. We're going to go technology within technology, seeing as the website's not working. Okay, this is nowhere near as good as I wanted it to be, but look what happens when I press start.
You can zoom in a bit more, sir.
Okay, so it did work, right? So I wish... This is so weird. But notice what happens. The blue one is going to move... Well, let's reset it first of all. The blue one will move down. The A one is going to move up, and it's going to still move a bit further. So let's just watch that again. Okay. So there it is moving, and there it is stopping as it gets to the top.
You know, if you make the blue one like bare heavy,
Yeah.
the red one like fly out.
Well, let's try.
Fly over. Yeah.
So bare heavy, meaning like, oh, that's my Bitmojis. 500. It's just going to accelerate really, really, really fast, okay? Do you see how it goes up much higher? It does go up much higher. And you'll often see in these questions it says it moves in such a way that it does not hit the pulley. Because if it hits the pulley, we get a bit of a crazy situation there, okay? So that was what the website was meant to be. And it's still not working, so... Okay. Right, so we're going to do some predictions with this on the next page. The next page that I'm going to want to do... I've given you a blank page to do it, is the question I'm trying to answer is how far does A travel before reaching its greatest height? So you know we talked about this bit over here when A was at its greatest height. This is what the part D or part E of the question would be asking for us to do. And I've put that in purple because it's going to correspond to the checklist of things we need to do. By the way, this is the hardest thing you'll do in Year 12 mechanics, okay? Yeah, because this is the hardest bit of that topic. Okay, so first of all, I'm going to do the orange bit. The orange bit is actually to work out, well, what's the acceleration of them and what's the tension in the string. This is like the bit that we knew how to do already. So I'm actually going to just work this bit out already. I'm going to work this bit out for the diagram we've got here. Now, we know that the mass of B is 5, so its weight is 5g. And the mass of A is 2, so it has a weight of 2g. We know that there's tension here, and we know that there's tension here. And we know that this one is going to accelerate downwards. This one is going to accelerate upwards. So I can go a little bit faster because we've already done one of these examples so far. And my checklist says, do F equals ma, and solve. Because I'm going to have to do an equation of motion, and then somehow I'm going to solve them. So to begin with, I'm going to look at B, and I'm going to resolve it up or down? Down, and I'm going to do an equation of motion. So I get 5g minus t equals 5a. Then I'm going to look at A, and I'm going to resolve it upwards, and I'm going to do F equals ma. What do you think the equation of motion will be, Ishak? For A? Yep. I'm going up, yep. Good. T minus 2g equals 2a. What's the quickest way of solving these, do we think? Add them up. So I'm going to do number 1 and number 2. And I'm going to do number 1 plus number 2. So that becomes 5g minus t plus t minus 2g equals 5a plus 2a. So here we've got 3g equals 7a. So we get 3 over 7g. And I'm just going to leave it in terms of g, a bit like Arisa mentioned. Oh, I didn't realise leaving it in g. I think leaving it in g is probably going to be a sensible thing if we can do. But if we want to, we can just see what it is as a number in case it's going to be easy to use later on. So 3 over 7 multiplied by 9.8 is just 4.2. So now we've got options. We can either use this or we can use this, whichever is easiest. Which equation is easiest for me to use to find out what the tension is, 1 or 2? 2. I think 2 is better because the tension here is just 2a plus 2g. So if I want to find out the tension, it's just 2 times, I'm going to go with 4.2. 2 times 4.2 plus 2 times 9.8, which is g. So times that by 2 and plus 2 times 9.8, and we get that the tension is 28 newtons. So that's the first part done. We've done the acceleration and we've done the tension in the string. Yeah. The 4.2 is because 3 over 7 times 9.8 is 4.2. Could have done it in terms of g. I've put both options in there just in case later on one of them is going to be more convenient than the other one. So that's all what you've been doing so far for homework and what we did last lesson. You did equation of motion, solve. Now though, we're going to have to think about some bits that come in this purple box, and this purple box corresponds to the next page that you've got in your booklet, okay? So you're still going to use this information that we've got here, but it's now going to correspond to what we're trying to do next. What we're trying to do next is find out how far does A travel before reaching its greatest height. So I'm going to have a look, and we're going to think this information that we've got here. Now, B, when it travels, actually no, let me stop for a second. Let me stop. We're going to fill in these bits of information along the bottom to begin with. We're going to fill in as much of that as we can do, and then we're going to think about the distances afterwards. So at this beginning stage here, what is the acceleration of both of the particles? 4.2. Okay, so it's 4.2 here. It's accelerating upwards and this one's accelerating downwards. And the tension was 28. This diagram is representing just as it arrives, just when B hits the floor. So what would the acceleration be there? It's probably going to be 4.2. It is going to be the end of the journey. The end of the journey there, it has an acceleration of 4.2. And because the string is technically still tight at this point, the tension is still 28. And I'm going to come back to why I've written this UA here as well. But at the moment, this is just as B hits the ground. It's still accelerating at 4.2, and it's still got a tension of 28 that we've got there. Hi.
Sorry, can I just give you those boys in here now?
Yes, Redwan and Hassan to the ILC at 3.
3.
Okay?
Yeah.
Cool. Now this is when B has hit the floor. What can you tell me about the tension or the acceleration here?
0.
The acceleration is not 0. The tension is 0 because look, the string has gone slack. So I can say here it is a slack string, which means that the tension is equal to 0. And we now want to think about what the acceleration is. So I'm actually going to remind us, what was the equation of motion for A? It was this, wasn't it? T minus 2g equals 2a. So F equals ma for A was T minus 2g equals 2a. But we know that tension is now equal to 0. So what does it look like we've got? We've got minus 2g equals 2a. So the acceleration is minus g. So the acceleration is minus g, or minus 9.8. Why is that ringing a bell? Because it's decelerating, that it's negative, good. But why is it minus g?
Because A is going up.
Okay, tell me some other things that have an acceleration of minus g. Yeah, it's the thing that's making it decelerate is its weight, and only its weight. Tell me other stuff when we've done it in the past. What has an acceleration of minus 9.8? Anything falling, anything free falling. A, although it doesn't look like it's free falling because it's got a string coming out of the top of it, it's free falling because there's no tension pulling it up anymore. So there's no surprise that A has got a minus 9.8, and that is because it is free falling, okay? What's the acceleration of A here when it reaches the top, when it reaches its peak? Still got an acceleration of minus 9.8 because there's still no gravity, there's still no tension doing anything to it. The tension is still 0, and I've said what is the velocity of A when it's at that top point? It's 0, okay? So we've now kind of gathered nearly all of the information that we need here. We're going to try and actually answer the question, which is how far does A travel before reaching its greatest height? Okay, so we need to know how far does A travel from here all the way up to here. That's what we're really trying to work out. What is the total distance that A travels? Is there any distance between these 4 diagrams that we've got here that we know about instantly? From here to here, how far has A travelled? That is 1 metre, because B has fallen down 1 metre. So A must have travelled up 1 metre. Now all we need to work out is this last part of the journey, which is from this point up to its maximum bit, which I'm going to call h for height. Now, you would not do this for every single question, okay? You're going to need to try and do this without all of these diagrams, but I'm trying to explain why these things are true to begin with. So, I'm going to try and take this scenario that's up here, and I'm going to try and take this scenario, which is from A all the way up to this bit, and I want to do some suvat that will help me find out what's happening. I know that its velocity here is 0. I know that its acceleration is minus 9.8. I want to find out how far it's travelled, so I need one more piece of information. What do we think that one more piece of information is going to be? The initial velocity. I'm going to find out what is its initial velocity here, which is going to be u of a. How do you think I could find out what its speed is at this point here? Do I know what its speed was here? 0, because it started from rest. Do I know how far it's travelling? Do I know its acceleration? 4.2. So could I work out what speed it's travelling at here? How? Suvat. Okay, so I'm going to do the very first thing that's inside my purple box here, which happens in nearly every single one of these questions. I'm going to do Suvat, and I'm going to find the final speed of A for this first part of the journey. And I've done a little arrow here, and I've said it becomes u. So I'm going to find out how fast is it travelling from here to here. And then in my yellow scenario, that is going to become the initial velocity. So we're talking about the velocity from here to here will be, I'm going to find out what its v is. That v will then become u for this yellow section that we've got. So I'm going to draw a line here, and we're going to do Suvat from, and you could either do the speed of b when b hits the floor, because the speed when b hits the floor is the same as the a is moving upwards. So we're going to think about from the start to when b hits the floor. We know that the initial speed is 0, and we're doing upwards as our positive direction. We know that the acceleration is 4.2. We know the distance that A and B are travelling in that time is 1 metre. And I want to find out how fast are they travelling at this stage that we've got here. So I'm just going to do, what's the connection of these things? V squared equals u squared plus 2as. So we get v squared equals 0 plus 2 times 4.2 times 1. So v is equal to the square root of that, which is just the square root of 8.4, which is not going to be an exact number, okay? So I'm just going to leave it as the square root of 8.4. That is this thing that we've done here. So this value of v is now going to become the initial speed for this yellow part. Hopefully that bit makes sense. So now I can say A's speed at this point is the square root of 8.4. I'm writing the square root of 8.4 to keep it accurate rather than writing it as a decimal, okay? Now all I need to do is the next thing in the list, which says find the new acceleration where t is equal to 0. And I think we've actually done that. Where did we do that on the board? This stage here, yeah, we found the new acceleration, which was here, and the calculations for that were here, where we said that t was equal to 0. So I've said find the new acceleration by making t equal 0, and it's free falling at minus g. So the next thing on our list is to do Suvat to find out this value of h. Remember, we're trying to say how far does a travel in that time? Well, we know from here to here is 1 metre. We need to work out that last bit there, which is h. So I'm going to do another bit of Suvat, and this is going to be from when b hits the floor to a's maximum height. The first time you look at this, it's going to be hard. The second time, it'll be tricky. Third, fourth, you'll get practice, and it will all just make sense. So we know that the acceleration is now minus 9.8 because we calculated there was a new acceleration because the tension had gone. We also know that A's initial speed was A's previous final speed. They're like two episodes right next to each other. The final speed now becomes the initial speed. hence me writing v becoming u. So u is the square root of 8.4. What else do we need? We need to find out what the distance is, and we know, what do we know anything about v? V is 0, yeah. Do you remember we said when it got to the peak that the velocity was 0? And I want to find out what s is equal to. So the thing that connects these together is, again, v squared equals u squared plus 2as. So v squared equals u squared plus 2as. So I get 0 equals, now you can see why I wrote it as root 8.4, because I'm going to square it. I'm just going to get 8.4 plus 2 times minus 9.8 times s. That multiplies to 19.6, and I put it to the other side. 19.6 s equals 8.4. So s is 8.4 divided by 19.6, which is 3/7 meters. Which means that this height here is 3/7. This height here was, what was that? 1. So we've done all of the things that the question wanted us to do. We did f equals ma, f equals ma, solve, suvat, new acceleration. Here's the new piece of suvat. The last thing that's on my checklist for me to do there is to solve the problem. So the problem asked me, how far does A travel before reaching its greatest height? A travels 1 3/7 of a meter. So A travels 1 plus 3/7, which is 1.43 meters to 3 significant figures. Now, this stuff that I've got here, these 4 diagrams and all of this information that I've got written here won't be necessary, okay? This was me really trying to break down what was going on inside this question. The working out was, previous page we did these orange bits. All we did here is we did suvat to find out v, which became u. We did a new acceleration. Why did we have to do a new acceleration? Why couldn't we use 4.2? Why couldn't I use 4.2 down here? Because the, what do you say, Shrek? The tension what? The tension is 0, the tension's gone, because B has hit the floor and the string has gone slack. So I had to have a new acceleration, and then I did a new suvat to give me some more information, and then the last thing I did was I put all of that information together to solve the problem and actually answer what it was that the question was looking for, okay? Hard, right? The question that I thought would be good for us to have a quick go at, yeah, why don't you actually try doing the next question that's on the next page if you want and you're not so sure about this. I'm actually going to do it and talk through it. If you want to do it yourself, you just do it yourself. I'm going to talk quietly through doing this next one, and if you want to just watch me do it, it's similar, and then we'll do some practice probably for the rest of the lesson, okay? So if you want to watch me, I'm going to do the question on the next page. Otherwise, you should have a go at it yourself. Okay. So we've got something similar to the last one. We've got their masses, 5m and km, and it tells you that k is less than 5, which immediately is making me think that one's going to be going down and that one's going to be going up. It just says they're connected by a light string, which passes over a small light fixed pulley. The system is held at rest, so it's starting at rest, and the hanging parts of the string are vertical with A and B at the same height above the horizontal plane. So these heights here are the same as each other. The acceleration is a quarter g. So that's a quarter g, that's a quarter g. And I'm going to add on, this is 5mg, this is kmg, this is t, and this is t. And I've put these 2 bits here are in orange because they're just the same as doing the equations of motion as we've done before. So I'm going to have a look at, to begin with, this one, because I have the most information about it. So I'm going to look at A, and I'm going to resolve downwards using F equals MA. So 5 mg minus t equals the mass, which is 5m times a. Oh, and a is actually a quarter g.
How is A approach?
Because it tells you in the question that the acceleration is a quarter g. So when I rearrange this, I get 5 mg minus 5 over 4 mg equals t. So that's 15 over 4 mg. That's my answer to the first question. Oops. Now I'm going to find the value of k by looking at the other particle. So I'll look at b and I'll resolve up using f equals ma. So I get t minus kmg equals km, and the acceleration is a quarter g. But I know that t is 15 over 4 mg minus kmg equals a quarter kmg. And I can cancel the mg's. So 15 over 4 minus k equals a quarter k. So 15 over 4 equals 5 over 4k. So k equals 3. And I'm just going to pause there for a second to give you all a chance to catch up to that bit. It's pretty tough. Okay, so pulley is smooth, tension equal throughout. Now we're going to go through the new part of the list. After descending for 1.2 seconds, the particle A reaches the plane. It is then immediately brought to rest by the impact with the plane. The initial distance between B and the pulley is such that in a subsequent motion, B does not reach the pulley. Find the greatest height reached by B above the plane. So I'm going to use my little checklist up here. I've got to find out the impact speed, because that's going to be used later on as the value of u. So I'm going to think about part D, and I'm going to do some suvat. I know that they start from rest, that they are moving for 1.2 seconds. They have an acceleration of a quarter g. Which is 2.45. And I want to find out its final velocity, because I know that I can use that to become the initial velocity, right? So I get that v equals u plus at, which is just 1.2 times 2.45, which is 2.94. So if I draw that diagram, we're now at a stage where that one has hit the floor at 2.94 and that one is moving up at 2.94. What does it say is the next thing on the list to do after we've done that bit?
equal to 0.
The new acceleration t is equal to 0. So if I look here, the one I'm interested in is b. So if I look at, in fact, either of them really, because they would have had the same thing. But if you remove tension from these things, I should probably do it with F equals ma again, really. But you would have no t, so it would be, oh, I've drawn the diagram wrong, haven't I? Diagram's the wrong way around. Should have been this way round. 2.94, 2.94. What do you think the value of the tension, the acceleration is? Now that it's gone slack, t is 0. Minus 9.8 because it's free falling, okay? So the new acceleration is minus 9.8, and that's because it's free fall. Or you could make t equals 0 in this equation that you've got here, and you could replace that with a and find out what it is. So the new acceleration is this. Now we know that its initial speed is the final speed. So the initial speed is 2.94. I'm going to highlight those in a colour so we can see that they've kind of switched places. That one has become that one. We know that the acceleration is now minus 9.8. What do you think I'm interested in finding out? Height, did you say? Yeah, height. So I need to find out what s is. And I know that v is equal to 0 when it gets to the top of that peak. So I get that v squared equals u squared plus 2as. So 0 equals 2.94 squared plus 2 times minus 9.8 s. So rearranging this, you get 19.6 s is 2.94 squared. And so s is 0.441 meters. So let's just think, that is telling me after this point here, it travels 0.441 meters. If I go back to my list now and I think about what I've done, okay, I did that, and I did that for the orange bits. I did suvat where I found v to make it become u. I did a new acceleration because the tension was 0, and I've done some suvat. I've now actually got to solve the problem. The problem says, find the greatest height reached by b above the plane. Well, I know that once this one has hit the floor and this one has got to here, I know it travels a further 0.441 meters. But how am I going to work out this distance here? Good. If I work out how far this one falls down, what can you say about these two arrows?
That one is 1 point. No,
They're not equal to each other because clearly this one is bigger, but they started at the same distance. So that distance will be the same as that distance, which is the same as that distance. So this distance is double this distance. So I need to go back and do an extra bit of work now to find out how far were they above the plane. Now, to do that, we need to go back to the initial problem. Why is it not letting me do that? So the last thing we need to do is how far above the plane. Yes, they were both at the same height. How far above the plane were they? Well, we're looking for what s is. Remember that the acceleration was 2.45. We knew it started from rest, and it took 1.2 seconds to hit the floor. So the distance above the plane is s equals ut plus a half at squared. So that's ut plus a half a t squared. So s is equal to, oh, and t is 1.2, sorry. Zero 0.5 times 2.45 times 1.2 squared. So s is 1.764. So that means this distance is 1.764. This whole distance here then is 2 times 1.764. And so the total distance above the plane is equal to 2 times 1.764 plus 0.441. Which is 3.969 or 3.97 meters to 3 significant figures. Now do you see why I said this is the hardest part of mechanics? There's a lot of stuff going on here. Okay, so we're going to try and do questions 1, 2 and 3 from exercise 10F. You've already done some of those questions. So if you have your homework with you, you can skip part A, B and C and you can just go straight in to what I call the purple part of the question, where there is V becomes U, new acceleration, more suvat, and then solve the problem. They're not always going to be about greatest height above plane. They're going to ask you other things, and you need to think about what it is that you need to do, okay? I've done 2 examples with greatest height above the plane. You're going to need to think about how it works best for you guys, okay?